can you see my change of slides?
Yes. By the way, Angelos just said in chat that people are coming, they're running a little bit late.
Okay, sure.
People are coming back from, of course, the continuation is beach.
Yeah, of course.
Actually, today I have a nice day.
Yeah.
Today, I mean, it's
Nice.
it feels like it's not summer, but it's still nice. And go swimming. The water is not bad.
Can you hear me?
Yes. Hi.
Just remember when you talk, if people have questions, you might hear me talking to you, or maybe raise a hand.
Yes. Please interrupt me if someone has a questions.
Just give us approximately 10 minutes, okay? Yeah. Okay. This one, how to post. Okay, so we will start with Bintu. It's our student from Northeastern, going to University of Edinburgh. He's going to talk about celestial Liouville theory or Young-Mills amplitudes.
Thank you. Thanks for the introductions. Thanks to the organizers for giving me the opportunities to present my talk on Zoom. The title of my talk would be Celestial Liouville Series for Young-Mills Amplitudes. It's based on this paper that came out last week with Stefan Stieberger and Thomas Taylor. Okay, so let me start with some motivation. So in recent years, there have been many studies on celestial CFTs, which purpose to be the dual description of S matrix in flex space. The central object of celestial CFT is the celestial amplitudes, which can be obtained from the four-dimensional scalar amplitudes for massless case by performing Manin transforms with respect to the light energies. And we have learned many interesting properties of celestial amplitudes. One obvious one is that the four-dimensional Lorentz symmetry is nicely encoded in the two-dimensional conformal symmetries of the celestial sphere, of the celestial amplitudes. We also learned many other symmetries, including BMS symmetries, CAD-Moody algebra, and W1 plus infinity algebras. Usually, we would say that the bigger symmetry, the better. It is because many problems can be solved by purely symmetry considerations. But it seems that the celestial amplitudes, celestial CFT is an exception because celestial amplitudes are over-constrained by the translation invariance in 4 dimensions. So let me show you some examples. So if we consider 1,3 signatures where we have a celestial sphere, then as we all know, the kinematic of massless scatterings force all the 3-point amplitudes to vanish. Then by this dictionaries, we immediately know that there's all the 3-point celestial amplitudes are 0 in this case. And similar things happens to 4-point case, where all the 4-point celestial amplitudes has a delta functions of x minus x bar, where x is the conformal invariant cross ratios determined by the 4 positions of these primary operators in CCFT. So this kind of delta function singularity still appears even if we go to 2,2 signatures. And this delta function singularity often creates some difficulties for us when we try to apply modern CFT techniques to the study of CCFT. And one can show that similar constraints persist in endpoint celestial amplitudes, which has been discussed in this paper. Okay, so this kind of delta function singularity motivates several groups of people to try to develop the following ideas. The idea is that we can try to break the translation invariance in 4 dimensions in controllable ways. What I mean by controllable is that we want to break the translation invariance in 4 dimensions, but we still want to keep the conformal symmetries in 2 dimensions. And this can be done in several different ways. For example, we can couple the Young-Mills systems to a dilaton backgrounds. In this paper, with a fan for Prober, Stieberger, and Taylor, we consider massless dilaton backgrounds. And in this paper by Casali, Melton, and Strominger, they consider massive dilaton. Or more generally speaking, we can consider celestial scattering in non-trivial backgrounds. And this has been discussed in these 2 recent papers. even though the equations in this or in all of these papers are different, but there's one common result of this calculation is that the resultant celestial amplitudes take the standard form of the low point correlators in CFT. For example, the 3-point celestial amplitudes in this case is completely determined by conformal symmetries on the celestial sphere up to a certain constant. And there's no delta function singularities appears in all these calculations. Another benefit of breaking translation invariance in this way, in these several ways, is that we might find some celestial amplitudes which can be related to non-CFT. So the goal of my talk today is to show you one simple example which illustrates this point. So let me first show you our main results, and then I will walk you through it in details for the rest of my talk. So we consider 3-level celestial amplitudes in a spherical diatom backgrounds, which is given by these expressions. Then we show that the celestial amplitudes in this case is given by the correlation functions of primary operators written in these two forms, where O minus is associated with the minus helicity gluons, and O plus is associated to positive helicity gluons. And these primary operators have the following interesting property, namely they factorize into two pieces. For example, if we look at this O plus, it contains a JA, which is exactly the WZW chiral current that we are all familiar with. And also it has these exponential operators, which I will show that it's the line operators in Liouville CFT evaluated in the limits of B goes to 0. And since we are all familiar with the current part, so my talk will be focused more on the Liouville part of the story. And once I'm done with the discussion of the Liouville part, I will come back to revisit the current part. So here's the outline of my talk. I will first briefly review the settings of gluon scattering amplitudes in diatom backgrounds and how we write out the celestial amplitudes in these diatom backgrounds. Then I will introduce Liouville CFT. I will talk about some basics of it, including semi-classical limits and line operators. Then I will show you how we can rewrite the Liouville correlation functions of line operators in a way that we can make contact with the celestial amplitudes in a specific background.
Can I ask one quick question going ahead? If you took the background to 0, so you got rid of the step function guy there, would you still be able to write your vertex operators in that factorized form, or that you rely on like the non-zero level that you're getting from that background for the JJ to work?
Yeah. We couldn't recover the I think we won't be able to recover the data function because for the Liouville for Liouville correlation function, we don't see any data functions appears in any limits so far. But it's a good question to maybe think about it in the future. So from the Liouville point of view, we don't see any data functions appears in certain limits. Okay, thanks for the questions. Okay, so we consider 4-dimensional diatom Yang-Mills series, which is described by these Lagrangians, where we have complex massless diatoms coupled to the gluons in these very specific ways. So phi couples to the anti-self dual power of the field strengths, and phi star couples to the self-dual power of the field strengths. We also introduce a source of the diatoms, so that the general gluon stirring setups is going to look like this. We have a bunch of gluons, and we use we use the source of the dilaton to supply background momenta to the Yang-Mills systems, so that the translation invariance in 4 dimensions is broken, but it's controlled by the background momentum of the dilaton. For simplicity, we will consider 3-level MHV amplitudes with 1 dilatons, and this has been computed in these papers many years ago. And it turns out that the MHV amplitudes with 1 dilatons is exactly the same as the Parker-Taylor formula for MHV amplitudes without the dilatons, which can be written in this helicity, spinor helicity variables in a very simple way. And without those generalities, we will always focus on this kind of helicity configurations where the first 2 gluons had negative helicities and the rest of them has positive helicities. And also in this paper, they show that because of these specific couplings of between dilaton and gluons, phi only couples to the MHV sectors and project out the MHV bar sectors. And we used, since we have a dilaton source, and the dilaton source is going to connect to the gluon systems via the propagator of the dilaton. So once we put in all of this together, we can write out the formula for celestial MHV amplitudes in the dilaton backgrounds by simply performing transforms with respect to the electron energies. We firstly done it in these papers, and it turns out that we obtain this formula, which contains 2 factorized into 2 pieces. The first piece is, we can call it the current part, which is purely holomorphic, written in this purely holomorphic coordinates, and exactly the same as the Parker-Taylor formula. And this current part contains all the group structures in here. The second part in this equation is the so-called scalar part, which contains all the Malin transforms in it. And as you can see here, the dilaton background is sitting here in the integral of the Malin transform. So our goal is to identify the dilaton background source such that the scalar path is going to take exactly the same form as the Liouville correlation functions in the semi-classical limits. So let me say a few words about the Liouville CFT. It's a 2-dimensional CFT that appears in many different places, including the original work of Polyakov, of the quantizations of the bosonic strings, and some toy models in the 2-dimensional quantum gravities. Or more recently, it appears in AGT correspondence, which relates certain class of Yang-Mills series to Liouville series. And many aspects of the Liouville CFT have been studied. It is considered one of the most well-known CFT besides minimal models and WZW models. One of the most celebrated formulas in Liouville CFT is so-called DLZG formula, which describes the 3-point correlation functions of Liouville primary operators. This was proposed by Don and Otto and Zamolodchikos back in 19th. Okay, so I will talk about some basics of Liouville CFT, starting from this Lagrangians of the Liouville CFT, where we have a usual kinetic terms plus the potential terms in this exponential form. The most important parameters in Liouville CFT is this B parameters, which is the dimensionless Liouville coupling constants. And also you can see here there's scalar parameters, which is usually called cosmological constant. And here I choose the background matrix to be fat, so that I didn't need to write out another terms which is proportional to the background charge of the Liouville CFT. But generally speaking, we need to consider the background charge at infinities, where the background charge is related to this B parameters in this way. And one can compute the stress tensors in Liouville CFT and show that the central charge of this stress tensor is related to the background charge in this formula. And one can show that the primary fields in Liouville CFTs are given by these exponential operators, where they are scalar fields with conformal weights given by these equations. So we will focus on the correlation functions of these exponential operators. In general, Liouville correlation functions of these primary operators are hard to compute by using post-integral method or by modern conformal bootstrap methods. But there's one exception for special configurations of the exponents when the sum of all the alpha is equal to Q minus M over B minus NB, where N and M are integers. Under these conditions, the Liouville correlation functions can be computed by Dovzhenko-Faddeev Coulomb-Gas integrals in a very specific way. So we are interested in the case of single integrals appears in the case when M equals to 0 and M equals to 1. And under these conditions, with these parameterizations of the exponents, the conditions we had on previous slides becomes these conditions of the sigmas. So we would like to compute the correlation functions between this V sigma B, and it's given by these conformal integrals. And notice that under these parameterizations of the alpha, the dimensions of the Liouville parameters are given by these equations, where we have a linear term depends on the sigma and the B square terms. And it turns out that if we want to make contacts with the primary fields in CCFT, we can take the limit when B goes to 0, such that we basically get rid of the second terms here, so that we can make a direct contact with the sigma i's and possibly I lambda that appears in the primary fields in CCFT. So next, I will talk about the limits when B goes to 0, which corresponds to the semi-classical limits of Liouville CFT. And recall that the central charge of Liouville CFT is related to the parameter B in this way, in these equations. So once we take the B goes to 0 limits, which is the semi-classical limits of Liouville CFT, the central charge of Liouville CFT goes to infinities. And remember that we are interested in the operators with this kind of exponents. And in this B goes to 0 limits, they are called line operators. And one can show that the correlation functions of these line operators are determined by the solutions of Liouville equations, which describe the metric on the sphere, but I won't get into that in detail. Remember, our goal is to rewrite the correlation functions in a way that it can be related to special amplitudes. So in these limits, the correlation function of these line operators takes these very simple forms known as the Liouville integrals with these constraints in mind. Okay, so we just try to rewrite the Liouville integrals as money transforms. And as I said before, we're interested in the MHV amplitudes with this helicity configurations. So we can try to parameterize, we can try to relate the sigma with I lambda subject to the sigma, to the constraint of sigma, and this can be realized in this particular choice, subject to the constraints of sum over lambda is equal to 0. Then the Liouville integrals we are interested in becomes this conformal integrals, which is the two-dimensional conformal integrals. And it turns out that we can use embedding space coordinates formalisms to rewrite these two-dimensional integrals into a four-dimensional integral such that we can rewrite it as a Marine transform. So let me say a few words about this embedding coordinates. The details are not very important. The main idea is that for each z on the threshold sphere, one can associate it with the coordinate x, which is a four-dimensional coordinates. Then the difference between two z's modular square is given by the inner product between these embedding coordinates. Then once we had this equation in mind, then use the Marine transform of the plane waves, we can rewrite the Liouville integrals, which is a two-dimensional integral, as a four-dimensional integrals given by this formula.
So one question, Ben, what
Yep.
is the solution for why the other helicity guys should be like shifted in their Louisville, like?
Yeah, so let me come back to the constraints here. So we need to fulfill these constraints for sigma. And then for the all plus, for the positive helicity guys, we want to treat it on the set footing, so that we assign the sigma in these ways. And what's left is the sigma 1 and sigma 2, which is associated to the minus helicity guys.
But you would think you could see that.
Then we find that in order to satisfy this constraint of sigmas, we need to assign a 1/2 to these two minus helicity guys, such that the sum of sigma is equal to 1. But we also want to have this kind of constraint, which is the sum of lambda is equal to 0.
Okay, so because I would have hoped that you could reverse engineer it and say like J has a given weight, and like I mean, like because the form of the MHV amplitude should be fixed by like the little group scaling. So is there any sense in which you're literally shifting the weights of the vertex operator, because like you want?
Yeah, we try different ways, but we find this is a nice way that it will give us the exact factorization forms between the, as I said before, it will give us a current part which factorize into this homomorphic forms, and then the Liouville part that I have been discussing here. So this, I would say that it's sort of unique in engineering, but it could be other choice. I'm not sure yet. Maybe it's a good question to think about in the future. Thank you. Okay, so yeah. So as Sabrina says, it seems that the negative helicity guys is quite special in this case, because all the positive helicity guys have the same integrals in the Marine transforms, but the negative helicity guys will have the shift conformal ways. But I think later it will become a bit clear in a moment. And also in these integrals, we have this expression here, and it's in the exponents. You might notice that the omega xi written in the embedding coordinates is actually the same as the momentums of all outgoing massless particles. So remember that we use the diatom source to supply background momentum to the Yang-Mills systems, and the background momentum is actually the same as the sum of the momentums of all outgoing gluons. And recall that we need to impose the constraints for lambdas. And once we impose the constraints in these delta functions, together with the Liouville integrals, we can write it in a very simple ways given by these equations. I will denote it as a equation star. So we can try to match the equation star to the scalar part of the MHV amplitudes in the dilaton backgrounds. Recall that the scalar part is given by these equations. So once we have the very simple equation star, we can match the scalar part with this particular choice of the delta. So as you noticed before, the dimensions of the all plus helicity operators is given by 1 plus I lambda. As usual, this is in principal series, but the negative helicity guys are associated with I lambdas, which has been shifting down by 1 if you start from a principal series. Okay, so we can match the equation star with this scalar part by this choice of deltas, and also by the choice of the dilaton source given by these equations. Another nice property of this source is that now the differential equations of phi zeros is given by these simple equations, and this represents a spherical short waves of the dilaton background field. And as a consistency check, we compute Liouville integrals for 3-point case and 4-point case by using our methods, which is the Marine transform, and they agree with the known results reported previously in the literature. So we are basically done with the discussion of the Liouville part. So let me revisit the homomorphic solve part of the story. And it turns out that we can associate the negative helicity gluons to homomorphic operators with -1 conformal weights. For positive helicity gluons, we can associate it with +1 currents that we are all familiar with. And this has been discussed by this paper of Costello and Paquet. They show that if we start from these 2-point functions between this J hat, then by using the OPEs between J and J hat or JJ OPE, we can compute these correlation functions between 2 J hat and many other J's given by this Parker-Taylor formula. And one comment about this is that it might look a little bit strange that this J hat has a minus helicity conformal weights. So it's unclear now for me how to put into these discussions into the framework of unitary WGW models. So this can be further studied in the future. So we basically show that the central amplitudes in the spherical short wave backgrounds is given by these factorization forms. So now we are in a position to connect the tree-level central amplitudes to the semi-classical limits of the Liouville series. We can introduce the following operators. For negative helicities, is given by this. For positive helicity gluons, is given by this. And consider the limits when b goes to 0. And in these limits, as I said before, the dimension of this O minus becomes I lambdas, while the dimension of the positive helicity gluons becomes 1 plus I lambdas. And by our discussion before, we have shown that the correlation functions of these primary operators is exactly the same as the MHV threshold amplitudes evaluated in the diatom background. And we also have done several calculations of these threshold amplitudes. One can check that it satisfies the BG equations for 3-point case and 4-point case. I don't have time to get into the details of the BG equations, but you can find some details from these original papers of BG. We also extract some OPEs from this threshold MHV amplitudes and compare the OPE to the non-OPEs in the literature. And we find that the leading OPE with 1/Z poles are exactly the same as the OPE as the non-OPE that we are all familiar with.
Sorry, can I ask one more dumb question? Is on that slide,
yeah,
J hat has dimension 1 or -1, and then J has dimension 1. Okay, so wait, J hat.
Yeah. Yes, please keep going.
+1 for J hat.
Yeah, this has J has -1.
Yeah.
And J has +1 dimension.
So I would have naively thought that in that expression, what you're doing, because the dimensions of J hat are like opposite, then basically you can track the shift in the weight you need in the dilaton field so that the O's that you've written down there are the same delta. Maybe I'm just confused about the.
Yeah, so we have some dimensions that comes from this J hat, which is -1, but we also have the dimension of the Liouville part.
Yeah.
And the dimension of the Liouville part is 1 + I lambdas in here, but because of the -1 here, together they have the dimension becomes the total dimension of O minus becomes I lambda. And for the positive helicity guys, this J has +1 dimensions, and the Liouville part has I lambda dimensions. So together they have 1 + I lambda. Does this answer your question?
Yep, thanks.
Okay, thank you. Okay, so the conclusion is that we show that the threshold MHV amplitudes evaluated in the presence of a spherical diatom short wave backgrounds are given by the correlation functions of primary operators that are factorized into homomorphic currents operators times the Liouville line operators in the limits of infinite central charge. So there are several questions we can try to study in the futures. One obvious question is that how to go beyond the MHV sectors. And another question is how to relate the Liouville short wave that we found here to the short wave that has been discussed in these two papers. And more interestingly, question is that how to relate what we found here to AGT correspondence. And another interesting question would be how are the quantum corrections to the threshold Yang-Mills amplitudes related to quantum Liouville series with finite central charge. So how many minutes do I have? Or so I will maybe I will stop here.
Yeah,
thank you for listening.
All the way to the one, yeah,
try again. Oh, there we go. Just a naive question. When you take the goes to zero, when you take the B goes to zero limit of Liouville theory, does that have a simpler description?
Sorry, could you say again?
Can that be just?
Can that be
as a simpler theory?
Sorry, the audio is not very stable. Could you say again? Or
Yeah, okay. So when you take the B goes to 0 limit of Liouville theory, does that have a simpler description? I mean, so for generic B, it's a complicated theory, but maybe in the limit B goes to 0, it's a bit simpler.
yeah, so yeah, it's there's an effective action of Straussian, and it will capture this limits of big infinite central Charles limits of Liouville, and we haven't talked about that. Maybe we can see if we can relate to some Straussian description of the Liouville.
I see. Thanks.
May I say something?
Yeah.
The limit B goes to 0 is a limit in which if you have these light one property of the limit is you have light operators which exponents scale together like are proportional to B. In this limit, the correlators of such operators are completely classical in the sense that you take the product of the correlator of a product, then you take it simply and evaluate it at the classical solution, which is given by the metric on two-dimensional sphere, and then you simply integrate it over all SL2C orbits. It's described in a beautiful way in the original paper of Zomological. It's a completely classical computation, a saddle point, you know, frozen, and so that's why these correlators, that's why light operators are so special.
Thank you.
I have a ignorant question. So why was it important that the dilaton background be a shockwave? Because you wanted, was it just because you wanted a bunch of delta functions on the right-hand side of the wave equation?
It's sort of like engineering things, and we want to we sort of want to have this we want to have these delta functions in the end in the central amplitudes, and it turns out that if we want these delta functions to appear in the central amplitudes, then we need to choose the shortwave background for the dilaton fields.
Okay.
And yeah, it's also the simplest. It's also the simplest ones that corresponds to these simple expressions of the Liouville integrals.
Thanks.
Any more questions? Okay, let's thank Bean again.
Thank you.
Okay. It's Alfredo. Let's try to make a small...
Yeah, I'm here. Let me just try to connect my screen.
Just give me a second to stop the recording and restart. Just 1 second, please.